Alright, Lecture 2, Real Numbers, Number Line, and Set Notation. In this video, we'll begin with real numbers first. Real numbers can be described as any number that you may have worked with ever since grade school, and ever since you have begun mathematics. Real numbers can be broken up into multiple categories, the first category being natural numbers. And with natural numbers, they are considered to be counting numbers. The first numbers you ever learned. So let's say number 1, 2, 3, 4, and 5. These numbers will be numbers that you will count on your fingers when you first learn mathematics. The next numbers after will be the integers. Integers expand upon these numbers into the negatives and also include the number 0, such as -3, -2, -1, 0, 1, 2, and 3. The last bit will be rational numbers. Rational numbers is described as a ratio of integers. The general form will be m over n. An example of that would be 1 over 2. The number 1 and number 2 are integers. If you do a ratio, which is 1 divided by 2, it gives you half. And you notice that with any two numbers you could put together, let's say 1 over 3, or 3 over 4, or 5 over 6, you can have any of these numbers be expressed as a decimal that is repeating in its case. So if you want to do 1 over 3, it'll be 0.333. 3 over 4 is 0.75. And 5 over 6 is just whatever the number is. Let's do a quick calculation for a sec for 5 over 6. 0.83. Repeating. And with each of these numbers, they have repeating decimals that you can predict consistently. So for here you have 0.3333, 0.75, and then there's also, you can put zeros infinite number of times at the end, and here you can put 0.833333. These are all under the category of real numbers, and for these three in particular, they all can be considered rational numbers. You can technically say that, because you can still describe each of these numbers as rational, because you can say, for example, number 1, you can express it as just 1 or 1 over 1, and it'll still give you the same number, 1, as with any number that happens to have a decimal, as long as it repeats the same value and is very predictable. On the other flip side, you have irrational numbers. Unlike rational numbers, these cannot be described as a ratio. Numbers that would be defined as irrational would be the square root of 2 and pi. If you recall from any level of math class that uses pi before, or at least introduced you to the concept of pi, the number will be 3.1415 and so forth. Notice how these numbers are not exactly consistent. It doesn't repeat 3.144444 or 3.14155555, unlike these numbers previously, which will make it irrational because these numbers will be unpredictable. And for the square root of 2, if we use the calculator again, for the square root of 2, you have the number resulting in 1.414213, and notice how, again, these numbers are not consistently repeating one digit. They're all changing. So you have a 4, then a 1, then a 4, then a 2, then a 1, and a 3. These numbers are all different, and it's not easy to predict, unlike the other ones in the previous section. With irrational numbers and rational numbers, and it's all other separate numbers such as natural, integer, and rational numbers again, these are all can be described as real numbers. Numbers that you can find on a number line. And this will be discovered in the next section. For the number line, it's the first thing you also was introduced as well as in, let's say, basic mathematics or even just high school in general. The number line is what describes the placement of values or numbers across the board, if you include integers as well. For example, you start with the line going far to the right and far to the left with extremes, with the middle being, let's say, 0. The right-hand side will be positive integers, positive numbers, 1, 2, 3, and 4, so on. And on the left-hand side of 0, you have negative numbers, -1, -2, -3, and so on. In between these numbers, you can fit in decimal values that can be described as integers, such as 0.5 or 1/2. You can put any decimals you want. You can even describe pi as well as irrational. Right here, 3.1415 ... or pi. At the end of the day, any number that you find on this number line can be considered a real number because you can find it on this number line. Later on in the course, you'll be hopefully learning something called imaginary numbers, where you can't find that number on this number line, hence it's imaginary. Either way, all you need to know is that this number line has integers, natural numbers, rational numbers, and irrational numbers that you can describe on here, and it will all be defined as a real number. In the next part of this series, let's see, you have the set notation. A set notation, well, we have to define what a set is. A set is defined as a group of numbers or a group of elements or collection. So a collection of elements. And an element is defined as some item that you can contain in a group, specifically a number. So in this case, it'll be using a number, like a number or member in a set. The mathematical notation for this will be A, comma B, with either parentheses, you can have brackets, you can have bracket on one of them, or bracket on the other one. The parentheses means it's exclusion. The brackets, or one of them at least, will be inclusion. The point of the set notation is to describe a solution set of numbers, or a group of numbers that will fit an answer to a specific problem. As an example would be, name all the numbers that will be multiples of 2 or all even numbers. And if you were to describe it in a set, you'll list out, okay, this set has 2, 4, 6, 8, 10, and it'll keep going up to infinity, where you have the set of numbers that begin from this number all the way up to infinity. And in this case, for an example, you would have parentheses to exclude infinity because infinity is not an actual number, it's a concept. And you'll include a number that happens to be, let's say, 0 if you started there, or 2. But for even numbers, 0 is like neither even nor odd. And that's the funny thing. So if you want to move it up, the next positive even number will be 2. Going for more expansion on this, let's just write some examples of numbers in sets to further cement this idea. Let's say with A and B, if you were to say, let's say, write examples, 3, 5 in parentheses. What this means is that you exclude 3 and 5, but you include any number that happens to be in between 3 and 5. Except you exclude just the number 3 and the number 5. So you can have 3.1, 3.2, 3.3, 4.1, 4.2, all the way up to like 4.99999, except you can't have a 5 or you can't have a 3. For brackets 3 and 5, it means you include everything between 3 and 5, including 3 and 5. So you can have the answer as 3 being the very lowest number and the highest being 5 as the maximum. Expanding it further to just one bracket and the other being parentheses, you can have the inclusion of 3, like any number you want, but you exclude any number that is 5 or above. On the flip side, if you want to do parentheses 3 or bracket 5, you exclude 3 or lower, but you include anything between 3 that is not 3 and up to 5. So you can have 3.000001 all the way up to 5. Now the next part, if you understand this already, would be something called unions and intersections. Let's start with union first. With a union, you have two sets that you would combine together to form a bigger set. A union will be a convenient way of making sets more simplified into just one big group instead of just 2 or 3 or 4 or 5 different groups. A union will be two sets, or I said 2 or more sets, I guess, to make one bigger set. An example would be if you were to find a union between, let's say, a set A would be, let's just erase this for a second, A. We have a set A that happens to have 1, 2, and 3. By the way, there's another way of writing down elements discretely, as in individually if you write it all out instead of just writing 2 numbers and just make it a range, as in the previous section. If you have a set A that happens to include the elements 1, 2, and 3, and a set B that happens to include the elements of 2, 3, and 4, the union of the sets A and B, which will be described by the symbol, this U symbol right here in the middle, is equal to all the elements that are A and B combined together, including repeating and non-repeating elements. So 1, 2, 3, and 4. That will be all the elements in both A and B that will be combined together into one big set, which will be the union of A and B, including numbers that happens to be the same in both, such as there's a 2 in A and a 2 in B, or any elements that are different, such as a 1 here but it's not there, and a 4 here but it's not in A. On the flip side, we have something called an intersection. Like a union, you have 2 or more sets who share elements to make another set. For this case, it might be a bigger set or a smaller set. Typically, it will be a smaller set since you're not taking every single number from every set. You're taking the numbers that just happens to be in both sets or in multiple sets at the same time. Using the example again of a set A being 1, 2, and 3, and a set B that happens to be 2, 3, and 4, the intersection right here will be represented by the upside down U, will be any element that will be both in A and B. So in this case, you have the number 2 in A and B, and the number 3 in A and B. Numbers 1 and 4 would not be included because 1 is only in A and 4 is only in B, but not in the other one. And the final solution would be 2, 3. Make sense? Okay. So you have intersections, unions, basic set notation understanding. Now we're going to go over something called the graphing part, where you graph your solutions, because that's another way of representing your solution sets. And we're going to go over just like the first section with sets, except we're going to use graphing this time. It will be graphing sets. Alright, so let's start with the very first basic set idea. So, with parentheses of A and B, the graph for this would be a number line. Just like the number line, this is where it applies again here. You have an A and a B. Since these two are excluding A and B, you draw open circles. Open circles means it does not include that value at A and B. However, it does include anything in between the two. So you create two circles at A and B to indicate where the solutions would be, but you make it open because it's not included. The next step would be to shade in between A and B, because the solution will be any number between A and B. Now the opposite will be if you include both. Similar to the first part, you have circles again at A and B, but they're filled because it includes the two numbers. Now if you only include A but not B, you only have one circle being filled and the other one being open. A will be filled and B will be open because A is included but not B. Flip side will be A and B. A is excluded but B is included. Just like the last one, but it's flipped again. Whoops. Give me a sec here. A has an open circle, B has a closed circle, and in between shaded. I think these are all the deviations. You have parentheses both, brackets both, one and the other. Okay, and then here's an extension of what we're going to be understanding for every type of solution set you have. There's also something called infinity, where you have negative infinity to positive infinity. There are parentheses because they're not actual numbers. You can't really count to infinity. You can say it basically is everything. This solution set has a special name, which will be called with the letter R that looks like a special R with the line at the end, which is all real numbers. Essentially, when you graph this, you write negative infinity, infinity, open circle, and then basically you do the graph, or you just write this big R right here and say any number in the number line is a solution. Extending from this, you have a lower bound that is negative infinity, but let's say an upper bound that is B, that will be included or excluded. So essentially B would be included in this case, and then the negative bound will be that way. So you shade down to the left since it's towards negative infinity. If you have excluded, same thing, but open circle, add B. And the last two would be bracket A, positive infinity, where you have A filled in, and your arrow is going to the right infinitely. And the last bit will be just like the last one, except it will be an open circle. A parentheses, infinity parentheses. And your graph would be A with the open circle. Let me redraw that. A with an open circle and everything being filled up to the right. And this about sums up everything what you need to do with basic graphing of sets, intersections, and unions. In another video, we'll be going over multiple examples, especially with special cases where you have some sets that have an included number and the other one has an excluded number, but they happen to be the same number, and we're going to figure it out and sort that out. And I'll see you in the next video.